Very good morning, everybody, for the last days of this exciting meetings where we are all gathering here. And I think today we have a lot of interesting talks, both on the progenitor emission side of FRB as well as on galactic talks. So we'll keep the day going with a talk from Vic from Northwestern Universities. Is talking about the FRB, connecting FRB to other cosmic transients. So Vic, what to you?
Yep. So hello, everyone. My name is Vic Dong. I am a grad student at Northwestern. And first, I just want to thank the organizer for this opportunity to talk about FRBs and their connections to other cosmic transients. I'm sorry that I cannot be there in person, but I hope this presentation can spark some discussion from afar. So without further ado, I'll just jump into it. By stating the obvious that despite hundreds to thousands of FRB discoveries to date, thanks to multiple experiments around the world, and knowing these defining characteristics about FRBs, the fact that they repeat, that they come from extragalactic distances, the physical origin or origins, if they come from multiple progenitor channels, is still quite mysterious. So there are so many possibilities as to where they could be coming from. And at the top of the chart, we have magnetars, or these highly magnetized neutron stars. We could have a system of binary neutron star that merge together. We could also have interacting binaries, or a system that involves an accreting massive black hole, or something completely different and exotic that we haven't even thought of. So by far, the prevailing model involves magnetars, and that's really strongly supported by the connection between FRB 2020-0428D that was discovered by CHIME, and it was connected to this galactic magnetar SGR 1935. What we also know about magnetars is that they're traditionally created through these very dramatic death of young and massive star, right? And it's manifested as these core collapse supernova explosions, which is a type of cosmic transient. Another really good example of this is the binary neutron star merger, which we know from the joint detection of gravitational wave 170817 and a short gamma ray burst 170817. We know that these type of systems can lead to fireworks of electromagnetic counterparts, including short GRVs, kilonova, and even multi-messenger signature like the gravitational wave event. So we've heard from Tarane earlier this week that you can use the global and local environments to get at the progenitor question. But I think another way to really look at this is to connect FRBs to other transients in which we know the physical origins of, to kind of provide these key insights into what might be producing FRBs themselves. Okay, so I am going to start at the high energy end and kind of work my way down the spectrum as we go along the talk. In the X-ray regime, I think this is especially exciting because it's the only energy band where an FRB counterpart has actually been seen from the galactic FRB case. So it's really kind of a gift that just keeps on giving. So this plot here shows the X-ray burst detected by integral, as indicated by the blue curve. And we see these three different peaks here. And then overlaid on top of that is the radio burst detected by CHIME. And we see the two sub bursts from this FRB roughly line up with the first two peaks in the blue curve, separated by a very small time separation of like just a few milliseconds, which is the X-ray counterpart of this FRB. And we know that galactic magnetars could have these giant flares or X-ray bursts. And we have seen this for galactic magnetars. So the natural kind of next step is to look for these X-ray counterparts for extragalactic FRBs. But I'm sad to say that there's been no high energy counterparts detected for any extragalactic FRBs so far, despite these really intensive monitoring follow-up campaigns. But there has been a lot of deep limits placed of these X-ray counterparts. There's a lot going on the plot on the right here, but I'm just showing the X-ray kind of fluence limit that's been placed not only for the non-repeating FRB population, which is shown here as the green triangles, but also the repeating FRB population in comparison to these other galactic magnetars. And so in this paper by Aaron Perlman, they placed very deep constraints for the FRB 2020-0120E that was localized to a globular cluster in the nearby M81 galaxy. And from this really deep limit, they were able to rule out things like ultraluminous X-ray source, giant flares, or even an X-ray burst that's similar to what was seen for SGR 1935. And the story is quite similar in the gamma ray, where there's really not been a significant detection associated with any of these extragalactic FRBs. So these upper limits are kind of compiled on the left here, on the figure on the left, where the data are taken by the Fermi Large Area Telescope, and each one of these are an upper limit on the gamma ray counterpart for an FRB at various time scales between 10 to 10,000 seconds. They also place constraints for the galactic magnetar case. There was a glimmer of hope, a very interesting exception here, where a gamma ray counterpart candidate was claimed for this FRB 240114A, which is a hyperactive FRB that also has a persistent radio source counterpart, which I'll come back to later in the talk. But here, what's shown on the right is that they saw these enhancement in the gamma ray flux at 3 different epochs in the direction of this FRB. So they claimed that it's associated with the FRB, which was quite exciting. But the same data set was actually reanalyzed by another team separately, and they came to the opposite conclusion in that there is no counterpart candidate associated with this FRB. So I think that really goes to show that it's not due to a lack of effort that we haven't seen these gamma ray counterparts. And sometimes it could be quite challenging to really even be able to detect these gamma ray emission associated with these FRBs. So all I've shown you so far are upper limits, which is not the most uplifting. But recall earlier in the slides, I've mentioned that short GRBs are linked to these binary neutron star mergers. So I think instead of looking for high energy counterparts to FRBs, we can also kind of flip this problem around and look for FRBs from GRBs that we already detect. So this is actually work done by Alice Curtin, where they looked for coincidence, spatially and temporally, of FRBs that were detected by CHIME between 2018 and 2023, and both short and long GRBs. And what they found is that there's no significant matches between the sample of FRBs and GRBs that they've looked at. But they were able to place constraints on FRB-like radio emission that may be associated with these GRBs. So if there were an FRB associated with the GRB, what could the radio flux be? And this is a really nice example from the paper for a GRB 210909A. Is a short GRB, and it was it occurred or was visible to CHIME at the time that it went off. So if there was an FRB associated with the GRB, it could have been detected by CHIME. So here are the flux limits that were placed for a FRB-like radio emission associated with this GRB. And because it's at a very high declination, they were able to monitor this for a long period of time as it transits over CHIME's field of view. And we can see that they placed these limits before the GRB, but also after the GRB event. So again, this is just another way to kind of think about connecting FRBs to these high energy counterparts. Okay, so currently there is no strong evidence for these high energy counterparts. What about the optical, right? There's a lot of efforts looking into these prompt optical emissions that may be associated with these FRBs, and they are predicted to kind of occur on timescales that are comparable to the FRBs themselves. In order to do that, you really want simultaneous or near simultaneous observations to these FRBs, which are good for targeted follow-ups of one, well-localized FRBs. Two, they're not too far enough to where you cannot detect these optical counterparts. And three, repeating FRBs so that you know exactly when to look when the FRB becomes active. So here is a really good example from Charlie Kilpatrick's work where they did this type of search for optical flash, prompt optical flash for FRB 2018-09-16B or R3. So what I'm showing here is the field of the FRB. And on the right is a single exposure from the Allo-PK high-speed camera that's mounted on the Gemini South telescope. With an amazing time resolution of 10 milliseconds. And again, there they see nothing, or they didn't find any optical counterpart. And I think currently the deepest limit on these type of optical emission comes from the work that was led by Daichi Hiramatsu, where they placed very deep optical limits for a sample of well-localized FRBs. And I know there's a lot going on the figure on the right, but what I want to show is that these deep limits, which are shown as these slanted lines, can already start to constrain these parameter space that's predicted by various progenitor models that they explored in the paper, which are these different rectangular regions. So we can see that for the deepest limit for FRB 220912A, which is a hyperactive FRB, they can already rule out some portion of these parameter space, which is quite exciting. Okay, so moving past the prompt optical phase, we can also look for optical transients that may occur on longer timescales if we widen our time window, such to optical transients that may be tracing the progenitors themselves. So we know that magnetars can come from core collapse supernovae. So if we can connect a supernova to an FRB, I think this would be a really powerful test to the magnetar progenitor model directly, right? So what's showing here is a diagram of in terms of time, where you see the supernova that's associated with the formation of the magnetar. And after some time, hopefully, you would see the first observable FRB. And I'll talk about this transparency time a little bit later. So a vanilla way to create this supernova is through the core collapse of massive stars. But you can imagine there could be a delay channel, such as accretion-induced collapse of white dwarfs, or something completely separate. But the idea is to kind of connect these supernovae to FRBs. And so I have recently kind of led the work to cross-match optical transients from the transient name server to a sample of FRBs that were localized by CHIME and its KKO outrigger to kind of do exactly this. And I know that Alice is giving a talk on cross-matching supernovae to FRBs as well a little bit later. So stay tuned for her talk. So what we found in our work is that there were no significant matches identified positionally or in terms of the redshift between any of the FRBs that we looked at and the transients that were on TNS. But that doesn't mean that we won't find a match in the future, right? So when we do, I think the more important question to ask is, how do we know that this would be a significant match? So to answer this question, I think it's important to kind of quantify the probability of chance coincidence, which I'm showing here on the y-axis as a function of the localization size for the KKO FRBs. And what we see is that it's very difficult to kind of claim an association is real beyond like about 2 sigma localization size, because beyond this point, it's very hard to distinguish between false positives and real matches. And so the way to kind of beat down these PCC values is to really have very well localized FRBs to do these kind of matches. And what that also implies is that if you do have a very well localized FRB associated with a supernova in the future, it will likely be very significant, right? Which is very exciting. So now coming back to the transparency timescale, which is basically the time separation between when the supernova happens to when we expect an FRB to emerge. This is really because the supernova ejecta is just too dense, right? It takes some time for it to become transparent enough so that the FRB can kind of propagate through. So to explore this aspect, I am showing the CDF here of the time difference between the supernova discovery or the optical transient discovery relative to when the KKO FRBs were discovered. So you can see that some of these are actually negative values. That means the optical transients were discovered after the FRB detection. And so from these CDFs, we can see that a large fraction of these, before this, the yellow band is basically a range of minimum transparency timescales that you would expect. So before that yellow band, we wouldn't really expect an FRB to escape, but after that, we would expect an FRB to kind of emerge from the supernova ejecta, and that range is anywhere between 6 to 10 years. And so relative to this yellow band, we see that a large fraction of these optical transients are actually too young to have a detectable FRB. But if you look at it on the flip side, the longer we wait, the more of these optical transients would reach an age to where the supernova ejecta would be transparent enough for us to detect an FRB. So there's a lot of potential there. And then if we go to the right of the yellow band, we see that there are some fraction of these optical transients, including these classified supernovae and core collapse supernovae that could already have a detectable FRB emission today. So in principle, we could be detecting FRBs from these optical transients. We also kind of explored the redshift space. So basically the redshift distribution of these optical transients that are currently in TNS. And these are the yellow curves here for different types of supernovae. And we see that most of these actually lies at a redshift below 0.1. It's a little bit higher or farther distance for superluminous supernovae. So we're really limited by our sensitivity to these optical transient, the supernovae. But this is going to completely change once Rubin LSST comes online, which should be imminently. And it's going to push that redshift all the way out to 1. And we would no longer be kind of limited by the sensitivity to these supernovae. And we can probe out to a much larger volume, which means we would also expect, the rate of these associations to be greatly boosted. So I'm very excited about Rubin coming online. So with Rubin sensitivity, we can probe out to higher redshift. How about the sky coverage, right? Where are they detecting these optical transients? So here I'm showing a sky map of all the FRBs that are detected with various different FRB detectors, including CHIME, DSA, CRAFT, MeerTrap. And then the cyan green circles are the patches of sky that was released in the data preview of Rubin LSST. And once Rubin comes online fully, which should be the end of this year or the beginning of next year, we would expect the entire southern hemisphere to be populated with these optical transients due to the very large field of view afforded by Rubin. And I think this is basically a love letter to southern FRB detectors, right? Like we should definitely be taking advantage of the fact that Rubin will be coming online in order to identify these sort of supernova FRB associations. Within CHIME, something I'm really excited about is that I'm leading this effort with Alice Curtin to kind of implement this alert system where we are basically cross-matching CHIME FRBs with all sorts of multi-wavelength counterparts under the sun, including supernovae, GRBs, gravitational waves. And we would have an alert system that automatically tells us when we do find a match. So this should be implemented fully very soon, but fingers crossed. Okay, so the last part of the talk, I kind of want to talk about these persistent radio sources that are associated with FRBs. They're not necessarily transients in that they do evolve quite slowly over time, but they are the only kind of multi-wavelength counterpart associated with FRBs so far. So this is the PRS that's associated with the very first repeating FRB, 2012 1102A. And actually, it was revisited by Mark Snelders and team, where they show that it's still compact, even years later. There's very loose definition for an FRB PRS, but it's essentially this constant radio emission that is not the FRB itself, nor is it the star formation that's happening within the galaxy, within the host galaxy of these FRBs. So in the past few years, there's been a very small increase in the sample size. So here I'm just showing a few examples from the literature where they found these other FRB PRSs that are also very compact, very bright, and coincident with these repeating FRBs. And in terms of where they come from, there are quite a few progenitor models, but here I'm just going to talk about two examples specifically where we think that PRSs are synchrotron radio emission coming from these wind nebulae. So on the left, you have these compact magnetized neutron star, could be a magnetar, that is releasing a lot of magnetic energy and kind of material into its immediate surrounding that's kind of blowing up this synchrotron nebula, which is what we see as the PRS, and it's inflated behind the supernova ejecta that initially went out when the supernova happened. Or you could have something like a binary system where a compact object, it could be a neutron star or a black hole that's accreting from a companion star through this accretion disk. And it's also launching a jet and releasing a lot of materials, again, into the surrounding environment through this wind, creating this huge bubble around the system called hypernebula, which is, again, what we see as the PRS. So something I haven't mentioned is that most of these PRSs are also found in dwarf galaxies. And if we look closer, we find that they're actually not the only radio sources observed in such environments. In fact, there are actually also other PRSs or other persistent radio transients in dwarf galaxies that are very similar to the PRSs associated with FRBs in both these individual cases and these sample studies. So something I did, an idea that I've kind of explored, is using these PRSs sort of as signposts for FRBs, right? So looking for other radio sources that could be a PRS associated with an FRB. So from this sample that was published by Amy Rines, where they identified these radio sources in nearby dwarf galaxies that are also offset from the galactic center, we did identify a single promising candidate that could be a PRS associated with an FRB. It was very compact. It was offset from the galactic center. It had all the observed radio properties that are consistent with the models that are out there right now. So it really is looking like an analog of FRB PRS. So as a fishing expedition, we also asked for time on GBT to look for FRB emission that may be associated with this PRS. The analysis for this is still ongoing, so I will know if there's a FRB very soon, hopefully. But beyond that, I think FRB PRSs may just be the tip of the iceberg. It seems like there's this whole new population of extragalactic radio sources in dwarf galaxies. And some of them could be linked to FRBs, some of them may not. So TARNA has this large program with the VLA where we're hoping to uncover more of these PRSs in nearby dwarf galaxies to hopefully build up a larger sample of these FRB PRSs, which would hopefully help us understand and characterize the diversity once we do have a much larger sample of these FRB PRS. So that brings me to my conclusion, and I'll just leave it up here and say that I think connecting FRBs to these other types of cosmic transients is a very powerful way to kind of constrain the FRB progenitors, which requires the systematic searches and multi-wavelength follow-up. And I'm really hopeful that we will find one in the near future. But until then, we will keep looking. So thank you very much.
Thank you, Vic, for excellent talk. It's open for questions, discussion.
So at the beginning, you said that one group found gamma ray emission from FRB and another group did not find. So what was the TS value for the group which found, and what are the differences? I mean, is it just background modeling which was different from the group which did not see it or not? TS is just the significance, I think, for me.
Yeah, I cannot remember exactly what the value that was quoted, but I think it was like significant enough to where they could claim these like flaring gamma ray enhancements. The other group just put out an ATEL. I don't know if they actually reported a TS, but their conclusion is basically that it was not significant. But I can check back to the ATEL and let you know.
Hey, I remember an earlier study where superluminous supernova, I suppose, PTF10 HGI, had a radio source that's very similar, a flat radio spectrum. Is there any such further studies where superluminous supernovae associated with this sort of PRS kind of sources?
Yeah. So this source, PTF10 HGI, is actually a radio source that was associated with a superluminous supernova that was led by TARNA. And so yes, there is that the is that the question? Is that if there are other?
Sorry, my question was, is there any other follow-up in that direction, and are there any other sources which are found associated with, I mean, how much is the SLSNE FRB association through studies of PRS? This is what I was trying to ask. I don't know if I was clear.
Are there searches of FRBs that are associated with superluminous supernovae?
Right. Yeah, exactly.
Yeah. I think I don't know of any specific FRB searches done for superluminous supernovae, but I know there's been kind of these associations because they all there are the FRBs that are associated with a PRS occur in dwarf galaxies, which is also where superluminous supernovae tend to occur in. So I know there's this connection. I am not aware of any ongoing like FRB search at the location of any superluminous supernovae, though.
So have there been any serendipitous observations of the FRB positions before they emitted bursts, and have we seen any like precursor emissions?
Precursor emissions in what wavelength?
Any wavelength. I guess optical or radio. Any wavelength, basically. It's just a generic question. Or has anyone done a study looking at the same positions, I think, before they burst? Before the FRB was detected?
Yeah, um I don't think there's been any sort of serendipitous detections. But I think there's been like cross matches done that's kind of looking for these precursor emissions that may be associated with FRBs.
Thank you. Any more questions? I have one. So I think you showed one of this plot where the debates optical counterpart follow up by Hiramatsu's group. And then I just, that plot looks kind of have a lot of information. Maybe if you can just say which part of the parameter space is kind of excluded by that limits. Yeah. This
Oh,
one,
this
yeah.
part. Yeah. Yeah, I think so these rectangular regions are basically what was predicted from these models. And I think based on the deep optical limits, they were able to rule out all of the parameter space above that, right? Because there was no detection based on their simultaneous optical observations. So it's basically everything like above that. And the limits are different depending on how deep you can get for each one of these FRBs. And the deepest was for 220912A.
So these are four different quadrant. How this plot goes like?
Yeah. So each one of these quadrants represents optical limits for one FRB. So this is 220912A, and these are for other FRBs. And then this one on the bottom is for SGR 1935. And then all of these slanted lines are the optical limits placed for each of these FRBs. And then the boxes in each of these quadrants are the predictions for each one of these events. And so you can just place limits for each of these FRBs. Does that make sense?
No, sure. So I think the galactic one and then the 2021, these two are actually having limit. Other two is still not there. Is that the way?
Yeah, I think other two are just not constraining enough to kind of rule out any part of these regions that are from model predictions.
Yeah. Thank you. Any further questions or anything from online? Okay. If not, let's thanks Vic for the excellent talk. Thank you.
Thank you so much.